All right, so we were talking about the following question. And suppose we have a sequence UK belonging to Sobolev space W1P from omega, which is in R2, R2 into R2, such that we have that the limit as k tends to infinity of integral of omega of distance to the power p of these gradients away from some set k, dx is equal to 0. I should also say, and k contained within M2 by 2, and that UK is tending weakly in W1P to some limit U. So recall that means that the gradients are converging weakly in LP, and for free that basically gives us that the functions are converging strongly, but we're basically interested in the gradients. So the gradients are converging weakly. Yeah? And my question was, does this imply that the limiting function u is such that the u belongs to k? Almost everywhere. So it's a Sobolev function, and derivative exists almost everywhere. Okay. So we started to do this construction where we did the following. So answer is no. If we have a comma b belong to k, such that the rank of a minus b is equal to 1, and that's equivalent to there exists v inside S1, because this is 2 by 2, such that a of v equals b of v. And then we did this construction where we have a square, where one side is parallel to v, the other one is perpendicular to v, right? And we started to layer in strips on which a function can take gradient a, and then b, and then a, and then b, and then a, and so on. Yeah? And I said, based on this construction, try and tell me why the answer is no in general for an arbitrary set k. Why is it the case that this hypothesis and this hypothesis don't necessarily imply that the limiting function has its gradient inside the set k? Okay, that's exactly what the weak limit is. Well, the way I've done this is it looks like these should be that these strips are equal length, right? So yeah, so let's denote each one of these guys as having thickness 1 over k. I'm not sure that's that readable, right? So construct sequence sequence UK with the UK looking like this, okay? And weak convergence, as I said, is equivalent to convergence by averages, yeah? So if you take an arbitrary set inside this domain, you know, and you think about what is the average of the gradients over this set, so I write that down. So weak convergence is convergence by averages. Converge So for, let's call this set Q, any set E contained within Q, we need to take it to have positive measure, otherwise nothing happens, then it's not that hard to see that if you just average the gradient of this sequence UK like this, then this is just going to tend to A plus B over 2. Yeah? Because we're cutting this into equal size strips, just by Fubini theorem, we have about half of these guys in the limit will be guys that come from strips A, and the rest will be from strips B, and therefore this is true. Yeah? So must have that du is equal to A plus B over 2. Yeah? But we don't necessarily have that A plus B over 2 is inside our set K, right? So this condition is not a convexity condition because we are not just taking any 2 points inside the set K and considering the line segment joining them. We're considering points A and B that are rank 1 connected, which means the rank of the difference equals 1. But if our set of matrices K looks like this, and this is a point A, and this is a point B, and there's a rank 1 connection between the two, well, it don't have to be right in interior, right? It could be like this. Then the average of the two don't necessarily belong inside the set. Yeah? And in fact, we could just set this up so that we have any linear combination of A and B inside these strips. So if we did, say, this was some different color, if this was lambda over K, and this was 1 minus lambda over K, like this, then we would create another average, and that average would be lambda A, 1 minus lambda B, right? So if any point of the line segment joining A to B is not inside the set K, then the derivative of du is outside the set K, and the answer is no. Okay. Do you guys feel happy with this? Does this make sense? Go ahead. Yep. Okay. Okay, thank you for this question. Yeah, so we did this when we set up A like this, and then B like this, yeah? And this is direction V, and 0 is right here. Yeah? We can exactly the same way do it in the reverse, right? We could have B up here and A up here. And that would work the same. Yeah? So the only difference when we do this kind of construction is we don't have this guy starting at 0. Yeah? So let's, if I can do this for something which is not actually going on 0, then do you agree that I can just do this, I can construct this Lipschitz function with all these layers? Yeah, so the line is always going to be parallel to V, but the only thing in this construction the only thing different in this thing that, sorry, the only thing different in this thing than this thing, at least as far as I can tell, is that these lines are not necessarily going through 0. But the issue of can we create a function that is continuous, which is not discontinuous across this jump, that issue is the same as this issue when we have AB or BA on one side or the other. So what I'm trying to, yeah. So if you're happy with this guy, and you're also happy when we don't center it on 0, then I'm thinking that this should be completely fine to you, because all we're doing is we're starting again, right? We can just like stick another guy up here. Yeah. So what this will look like is something like this. So this is the reference domain where we put in the strips A, B, and let's, for simplicity, take A just to be the identity matrix, and let's take B to be something that is rank 1 connected. I don't know. B to be, I don't know. I don't want to come up with anything. I can come up with something. No, let's not be weak. So yeah, let's take a diagonal matrix like this, A, 0, 0, A to the minus 1. So this is something that's sending the ball into the ellipse like this. For sure, there is some line which is sending it to something of length 1, right, for this matrix. B of v equals 1, yeah? And therefore we can rotate, so we actually don't need this, we need a rotation. So let's take a rotation like this, some rotation, and then this guy, and then we take some rotation such that A of v equals B of v, because this is a unit vector, so we can rotate any unit vector to another unit vector. So we get A is a rotation and B is a diagonal matrix. Concrete example, yeah? So if that's matrices, we do A, B, and then the A's are just rotating everything, so we see exactly the same thing like this. And what does the B do? B is a skew, is skewing things off to one side like this. And then again, A is doing this, and then B is skewing things off to one side like this. Or maybe the other side, but that's the action of B. Yes, but so this is, I mean, I think we're talking about the same thing, but this is how I would express it. If you take any if you take any point here, whatever U is mapping this point onto, say it's mapping onto this point, then by the fundamental theorem of calculus, as you integrate along this direction V, then you have the two coordinates of your function, U1 and U2. Yeah? So du acting on V is given by the first coordinate dot product V, second coordinate dot product V, right? That's what matrix action is. And as we integrate along this thing, then these guys will behave the same way whether or not we have A or B. They lift off in the same way, you know, in a consistent way. So both coordinates are sticking together, whether we, let's express it this way. Suppose we start just a little bit inside here, so we're actually in B, and we start a little bit inside, so we're actually in A. Yeah? Then both of these guys they won't detect the difference between being in A or in B. So the fundamental theorem of calculus will lift us off from this starting point in the same way, both coordinates. So they don't rip apart. Yeah? That's how I'd like to express it. It's a lot of, so when I was learning this subject way back in the day, it was a mental shift for me to think about functions from Rn to Rm or R2 to R2, because I was so used to thinking about scalar valued functions. And that's the kind of mental jump you can go to. You can also just mess around with the algebra. So look, if we have A minus B is rank 1, then we can write it like this. Like this, yeah? So let's subtract, so let's subtract A plus B over 2 from this entire matrix, from both sides. So then we're going to have here, we're going to have, A minus B over 2. And then here we're going to have just minus this, so minus A minus B over 2, like this, yeah? So that's just doing an affine change of coordinates if we just subtract a fixed matrix from everything, yeah? So then we have these rank 1 matrices like this, yeah? And the rank 1 direction is direction in which these things agree. So that'll be in the perpendicular. So what is matrix A? This is A1, B1, A1, B2, A2, B1, A2, B2. And the direction V, which agrees for both these guys, is the orthogonal direction to B, right? Because if we test B, or the orthogonal B of this, it's B on B perp, this is equal to 0, just from this. Yeah? So B is, or B perp is this direction, and B is this direction, like this. Yeah? And then as we're going in, so for sure they agree along these lines, because both of these matrices are being killed by B perp, right? So they definitely agree. In this case, we've replaced these matrices A and B with these rank 1 matrices, and the image is no longer a solid thing. It's a one-dimensional thing. It's a one-dimensional line. And it definitely agrees as we go along this rank 1 direction because of this little calculation, right? And if we go in the orthogonal direction, which is if we go up in direction B, then what we're going to have? We're going to have A minus B over 2 acting on B is going to be this vector valued function given by minus a half A1, A2 mod B squared, and then this guy A minus B over 2 will be a half this vector A1, A2 mod B squared. So as we travel up this direction, then we are doing this jagged line which goes in direction A for a bit and then in minus direction A for another bit. The best way to get a good feeling for this is to do this little calculation yourself. So just take in your memory the fact that, okay, if I have something like this, then I can just subtract, like I said, change of variables, which was wrong. I can just subtract an affine function. Just subtract an affine function, which is just given by something which got gradient A plus B over 2. Yeah? And then you will see that the gradients now turn into these gradients. Yeah? And then explicitly write out what happens as we go in direction B perp and what happens in direction B. And you'll come to the conclusion that this thing is doing something like this. And you can fit it together in a perfectly continuous way. So we've got the statement we want. So it's definitely not true if we have a rank 1 connection and the entire line segment is not contained inside K. Okay, let's consider a different question before I raise the board. What about if instead of asking if the limiting function belongs to K, what about if we ask, does this sequence of gradients converge strongly, not weakly, strongly in LP to the limiting function? So it converges weakly in the sense of averages. That's in our hypothesis, and that comes for free for any bounded sequence in W1P just by the stuff we were talking about. Now the question is, does the gradients converge strongly? And first question, is this a weaker or a stronger question than the first question? Is this a weaker or stronger question than the question of whether or not the gradient du belongs to K? And second question, is this always true? And obviously if it's a stronger thing, then the answer is no. Yeah? And if it isn't always true, what is the counterexample? Yeah? So first determine if this is weaker or stronger, and then try and tell me if we know how to build a counterexample from the stuff we were thinking of. Okay, the first question about weaker or stronger is the easier one, but first understand that and then try and understand the second thing. What are your answers? Okay, it's stronger. So if we have that the UK tends in LP to du, and we have the hypothesis that the distance of P to duk K tends to 0 as K, little k tends to infinity. Then suppose that the u does not belong to, does not belong to K almost everywhere, i.e. there exists a bad set B contained within omega positive measure such that this is true, so there must be some non-trivial distance, so we're going to take a subset where there is some non-trivial distance bigger than delta. So such that the distance of du of x, the k, is bigger than delta for all x belonging to B. Are you guys happy with if this is not true, then there must exist a subset B such that this is the case for some delta. This delta. Are you guys happy that such a set B and such a small delta must exist if this is false? If this is true, almost everywhere, yeah, then well, I should do this implication. Then there exists, because if, let's call this thing star, star is the case, there exists a set pi such that du of x does not belong to k for any x belonging to pi, and the set pi has got positive measure. Right? That has to be the case if this isn't true. Yeah? And then this set pi can be decomposed as follows. So let bk be this set of x belonging to omega such that the distance of the gradient away from k at this x is bigger than 1 over k. Yeah? Then pi has to be the union of all of these guys. Right? Because for each one of these guys, each one of these x inside pi, then it's not inside k. I should have said that k is closed, otherwise that doesn't make sense. So let's take k to be closed. Okay, apologies for that. Yeah, I'm taking k to be closed. So if we are not in k, then we are some specific distance away from k. Yeah? And therefore, that distance is bigger than 1 over n, or 1 over k for large enough k. So we have this decomposition. Yeah? And therefore, this set is an increasing collection of sets, right? So so if we have some guy belonging, so if k1 is bigger than k2, maybe the other way around is better, k2 is bigger than k1, then b of k1 is contained within b of k2. Yeah? So the measure of this thing is the limit as k goes to infinity of the measure of this thing. Yeah? And therefore, one of these guys has to have positive measure. And that's our set B. So all I need is that k is closed. Okay, pleasure. Okay, cool. All right, so are you all happy that that we have some set B with this property like this? Yeah? Speak up if not, because we have time, and the point of this is to take everybody along. Everybody happy? Give me a thumbs up if so, thumbs down if not. All right, cool. So there exists such a set B, and then let's do the following. So look, if we do the integral of omega of the pth distance of du away from k dx, say 1 over p, then this is bigger than some constant over the set b of the pth distance du comma k dx 1 over p, right? And then by definition, this is bigger than the measure of the set b times delta to the p. Yeah, everything to the 1 over p. So there is a constant, which is this thing. Yeah? And then this is delta, like this. In the 1 over k0, yeah. But in the initial statement, I just said, yeah, I just said that this is true, and then this is the expansion, and I didn't specify, but yeah, delta is 1 over k0 in this case. Yeah, cool. So this guy is definitely bigger than 0 because the measure of b is bigger than 0, delta is bigger than 0, so we have that this is strictly bigger than 0. Yeah, and we know that the gradients converge strongly. So we're showing that the statement is stronger, so we're going to conclude that du belongs to k from the assumptions that the gradients converge strongly. Yeah? So if the gradients converge strongly, then we have this is true. Tends to 0, as that's the statement of the gradients converges strongly. Yeah? So since this guy has this property and the LP distance between the gradients of uk and u are tending down to 0, then there exists some n such that duk minus du to LP omega is, say, less than half of this, 1 over 2 for all k bigger than n, yeah? Just a statement of limits, right? So then, like this, right? That's what I think you were saying, yeah? Yeah, okay, thanks. So, doing this the right way around, we have this, again, it's the same thing, it's the triangle inequality, yeah? And we know that this thing is small, so this is less than whatever, 1 over 2 b 1 over p times delta from this thing, because we've taken k to be large enough, and this thing can be as small as we like. Oh god, let's get it right. So this thing is small, this thing is small, which controls this thing, which is this thing, which gives us this. And then this thing is as small as we like because our hypothesis is that this thing goes down to 0, yeah? So for k large enough, then this thing will be less than this as well if we wanted to. So say plus 1 over 4 mod b to the 1 over p delta. But then this is contradicting the lower bound that we have, that this thing is bigger than this. Everybody happy? Cool. So what we have is that if the gradients converge strongly, then the limiting function du has to be inside the set of gradients. Yeah? So gradients converging strongly is a stronger statement. And therefore, the answer to our question, is it the case that we arbitrarily have that under this hypothesis, the gradients okay, let's write it again because that statement is completely different. So if we have that this thing, du k dx tends to 0, the question of does this imply that for our subsequence that is converging weakly, so let's write that, so uk converges weakly in w1p, does this imply that the gradients converge strongly in LP? It's stronger, and therefore Thus, it's not true in general, right? It's not true in general. It's a stronger statement. It's not true in general. Yeah? All right. And let's now think about what counterexample can we build using the techniques we've learned to show that this is not true arbitrarily. What is the condition what is the condition that if we see it holds true, then we can kill this from being true straight away? Okay. Okay. So recall in the previous situation when we were asking, does the limit du belong to K? Then the condition was that we had some A and B inside our set K where the rank of the difference was 1. It's a rank 1, what we call a rank 1 connection. And the entire line segment wasn't inside K. That was the condition. Yeah? Yeah? So if we had a rank 1 connection and the A comma B is not contained within K, then it's not the case that the gradient belongs to K necessarily. We can build a counterexample. My question now is, what is the condition to make this false? So this condition for sure is enough. So if we have a rank 1 connection, I should say no. If we have a rank 1 connection and line segment's not contained within K, then that condition is enough to kill that because this is a stronger statement, and we know that gradient belongs to U. Gradient U belongs to K is false when we find this. Yeah. So this condition is enough to kill this statement. Do you see what I mean? Yeah. Now my question is, do we need this full strength of this condition, or is there anything less than this that we need? Do we need something less than this to kill the condition? So think about what we just did in terms of counterexampling the first statement, and then think about if we need the full strength of this being the case for us to counterexample this one, or do we need a bit less? Think about that while I erase the board. Okay, let's reverse it. Let's say, do you guys have some impression of how we can build a counterexample in any way? Forget about what are the sharp conditions. Do we have a way to build a counterexample using the stuff that we know? But the hint is that I've only shown you one thing, right? And that's to build this kind of construction like this. Right? This is the only thing I've shown you, is to build. These are called laminates, by the way. These are the laminate function. I'm going to send you some reference to this kind of stuff. Put that in the syllabus maybe. So this is length 1 over K, and we do A, B, and so on. Yeah? And we construct our sequence of functions UK such as this. So UK from omega into R2 such that the UK looks like this. Yeah? That's our construction. Yeah? That thing for sure satisfies the property that actually integral of the distance to the power p of this sequence away from k dx is equal to 0 because the gradients are just a or b almost everywhere. Yeah. Yeah. So satisfies the hypotheses. We know by these abstract theorems that we have a subsequence that converges weakly in the sense of the gradients will converge weakly to some limit. Yeah. Yeah. And we've just discussed that weak limit will be this function u such that the gradient takes the value a plus b over 2. Yeah. And the UK tends weakly in LP just to du, where du is equal to a plus b over 2, like this. Yeah? So, does this example kill strong convergence? So, do we have that du k of x minus du LP tends to 0? And the answer, as you can guess, is no, right? But why not? Why is this false? Well, look, if we have duk of x minus du of x, then this is exactly the same as duk of x minus a plus b over 2, because the gradient is just a plus b over 2, yeah? And then du of x, if it exists, so this sequence of functions has gradients existing except on these lines, but if the gradient exists, it's either going to be a or it's going to be b. That's the only two things these things can be, yeah? That's the construction, yeah? So if the uk of x equals a, then we have a plus b over 2, which is a minus b over 2, like this, yeah? And if the uk of x is equal to b, then we have b minus a plus b over 2, which again is a minus b over 2. Yeah? And a and b are not the same, so we have that this thing, the integral of this thing is just a minus b to the power p integrated over domain square rooted by 1 over p, or rooted by 1 over p. Yeah? So then this thing is definitely not the case. This thing is actually bounded below by a minus b over 2 times the well, actually I'm not going to say what it's times by, let's just figure it out. So we have integral of omega duk minus du, the p dx, 1 over p. This thing is equal to just the measure of the set like this, and then just a minus b over 2, the 1 over p, yeah? Oh, to the p to the 1 over p. One over p, and therefore this is just equal to this set omega 1 over p, a minus b over 2. And so it's always bounded below uniformly, right? So we've taken our a and b, they are different, so we have a uniform bound. So it's definitely not the case that this tends down to 0. Yeah? So our construction kills strong convergence of gradients. Yeah? Everybody with me? Cool. All right, so what did we actually need in this construction? What did we need? What did we need here? Yeah. So we definitely have that. So let's call this thing star. So star is false. And all we needed was that there exists a comma b belong to k with the rank of a minus b being equal to 1, a not equal to b, i.e. what we call a rank 1 connection. In K. So it's less, it's a weaker thing. So previously we needed a rank 1 connection, and we needed the fact that a line segment connecting A to B or joining A to B is not inside K everywhere, right? Now to kill compactness, which is a stronger statement. We just need to have that there exists a rank 1 connection. That's all we need. Inside the set K, yeah. So previously we had that there exists R1 connection, and the connection, the line segment is not inside K, like this. We need both these conditions, and then with both those conditions, we can kill the statement that the gradient belongs to K. But to kill the stronger statement that we have compactness, we need less. We just need that there is no rank 1 connection, which makes sense. To kill something stronger, a weaker condition is what you would expect. Cool. All right. Pleasure. So the naive guess would be that if you don't have a rank 1 connection inside your set K, so I am overrunning, I'm going to state this, if you have to leave, just leave. The naive guess is that if you don't have a rank 1 connection, perhaps you will have compactness. Perhaps you can actually get something to work, right? And that's also not true in general, but it is true if you have a connected, a closed connected set K inside 2x2 matrices. And this is a theorem of Sverak from 93. So Theorem 93, Sverak. So if we have that UK belongs to W1P, omega into R2, K is contained within M 2x2, and closed, connected, and no. So rank 1 is now R1 connections. Then if we have the gradients are getting closer and closer to the set K, and we have that this sequence is tending weakly, and this is not a strong hypothesis because, as I keep saying, we get weak convergence very easily just from having a uniform bound on the Sobolev norm of a sequence of functions. There exists a subsequence that converges weakly. So if we have that the UK is tending weakly in W1P to U, i.e. the gradients converge weakly, then actually the gradients converge strongly. Okay, then the gradients converge strongly. So, in particular, the U belongs to K almost everywhere by the argument we've just seen. So, if you're in 2x2 and you have a set K that is closed and connected, then somewhat surprisingly, this thing is true, that this simple, well, for me, or for you guys, maybe it seems quite intricate, but as you play with this, it's going to seem rather simple. This simple counterexample, if you can exclude that by not being able to begin it, by not having a rank 1 connection, and it's closed and connected, then weak convergence becomes strong convergence. And this is an example of something called compensated compactness. So if you type in compensated compactness into Google, you'll see thousands of things because this is a huge area inside PDEs. But the simplest manifestation of this is exactly this theorem, and the simplest, but also actually one of the deepest, because this question in general is not well understood. And this is part of one of the papers I want you to collectively decide to read and present on. This is a paper by Sverak called Tartar's conjecture. So just type in Tartar's conjecture into Google, Sverak, and you'll find this paper. Tartar's conjecture was about when is this weak convergence turning into strong convergence, and this is a specific instance of it. And the moral is that the structure of K is forcing this sequence of functions that are converging, whose gradients are converging weakly, to actually converge strongly, to improve from weak to strong. It's completely false if you just have a sequence of matrix-valued functions. It has to be gradients. And as we've seen, it's completely false if we have a rank 1 connection inside the set K, right? So this is a very neat, simple to state theorem, and it's actually quite easy to prove. This is typical Sverak proof. It's a very neat, clear idea that does this without too much technical difficulties. And yeah, it's a very important theorem for the things we're going to discuss on Friday and next Monday. All right, that's it for today. Okay, cool. So please watch over this. Send me your questions if anything's unclear, and we'll continue talking about these issues. I will tell you about the other theorem. There's 3 papers I suggested. I'll tell you about the other one and more about this paper. And that'll be what we'll do on Friday. All right, see you then. Bye-bye, people.